This video is going to be a walkthrough of an exponential growth decay situation. It's talking about bacteria growth, which is a pretty common application. Before we start, low tech, you guys know what my phone looks like. I don't even have a smartphone. I get it, just not willing to spend money on the technology. It's not that I can't use tech, it's not the money, but anyway, whatever, not going to launch into that right now. Please ignore the big bright blob that is right there. I will try to avoid that spot, so I apologize. I know that's distracting on the video. Anyway, so here's a problem that I took a picture of directly from your text. It is on page 390, I believe. It's number 40. And what it says is the number of bacteria N in a culture is modeled by N equals 100 times e to the kt. So I just rewrote that equation right there, where t is the time in hours. So N is the number of bacteria, t is the time in hours. What the heck is k? Anyway, if N is 300, all right, that seems useful. When t is 5, okay, so they actually give me some information about the size of the culture. Estimate the time required for the population to double in size. So I really want to know, when is this population going to be twice the size that it is initially? Well, looking at this equation, it seems to really be that y-intercept, that vertical stretch factor for the exponential function. So that 100 really seems to be the initial value of bacteria. So I'm really trying to figure out, when is the number of bacteria going to be 200? Double in size. Double N equals 200. And that might become useful. So anyway, if I want to know when N is 200, I mean, I could put in 200 here, but then thinking ahead, I notice that I still am missing k and t, two variables. It seems problematic. I really need to know what k is. So that the only thing I was missing was time. So I need to figure out k somehow. It seems to figure out k that I would need to know both n and t, because then I would only have one variable in this equation, and we're pretty good at solving those. And if I look over here, I do have some information about n and t that are simultaneous. So I can use this data maybe to figure out t. So let's do that. If I come up here, I'm going to do this in black. We know that the bacteria would be 300 when the time is 5. So I would really have 5k there. T is 5 and then n is 300. And so I could start to solve this. Realizing I want to isolate for k, I really need to get rid of all this other stuff. Let's get rid of the 100 first. So divide both sides by 100. We're going to be left with 3 equals e to the 5k. And I'm really trying to find the exponent. That makes me think of logs. Ways to find exponents. You know, logs will invert the, or are the inverse of this exponential function. So I can use a log to rearrange this, or I can rewrite it with a log, or I can apply a log to both sides to cancel out the exponential. However you want to think about it. I'm just going to change the form. So I really know the exponent, 5k. That is the exponent on e, log base e, that made 3. So what's the exponent on e that made 3? Well, it was 5k, just changing the form. Or I could really, apply natural log to both sides. Like I said, if I wanted, I'm going to rewrite that as natural log because I like to see it that way better. It's just more efficient. Just wanted to do that for you guys so you can see that. But I want to solve for k, so I need to get rid of 5. Well, that's easy enough. We get k equals the natural log of 3 all divided by 5. Which means this equation can be written as n equals 100 times e to the, there's k, ln of 3 divided by 5, t. And I want to figure out, okay, so now that I found K, I want to go back to the problem. When is this population going to double in size? When will n be equal to 200? So I can replace that. 200 equals 100 multiplied by e to the ln of 5 over, ln of 3, I lied, over 5 multiplied by t. Now this looks just like the problem I did before, so I could really just keep going. I would encourage you to pause the video and do this on your own. But I'm going to keep going now that I've told you to pause. I could divide both sides by 200. 2 equals e to the ln of 3 divided by 5 multiplied by t. That 2, why does that make sense? Well, I want this whole thing to be 2, which means this whole thing would have been 2, which means the multiplier on 100 would have been 2, so we would have multiplied 100 by 2. We would have doubled 100. We would have doubled the size. It makes sense that if we're trying to double the size, we want our multiplier on our initial quantity, we want the multiplier on the quantity to be 2. If I wanted to triple it in size, I would want that multiplier to be 3. Oh, like that, tripling the size. So we can see that this actually makes sense. Now again, now that we've discussed why it makes sense, let's keep going with solving. I can rearrange the form again. Remember, what's the exponent on e that made 2? Well, it happened to be ln of 3 divided by 5 multiplied by t. So, again, that was for you guys. So that's really ln of 2. Solving for t, ln of 2, I'm going to multiply both sides by 5, divide both sides by ln of 3, or just multiply by the reciprocal of ln of 3 over 5, and that equals t. And if I type this into my calculator, which, oh, by the way, that's ln of 2 times 5, maybe I should write that as, just so I don't get confused, but if I type this in my calculator, 5 multiplied by the natural log of 2 divided by the natural log of 3, not 39, 3.155 approximately. And that's 3.155 hours. So essentially we're saying that the number of bacteria would double in size in 3.155